In most cases, loadings on beam are permanent and therefore, the analysis for the reactions and internal forces developed in beam is straightforward. When encountering moving loads, as what we may see for a bridge, we need to inspect the correlation between the load position and the resultant forces in member. This is when influence line diagram is produced. Let us develop influence line diagrams for a simply supported beam. The process is simple and applicable to other types of statically determinate beam. On this beam, we load it with a unit load located at a distance of x from our origin, the support A. The length of the beam is L. By taking moment about point A, a function of By with respect to x is produced out of the equilibrium equation. Then, by taking equilibrium in y direction, we obtain a function for Ay. With these functions, we are good to construct influence line diagrams for reaction Ay and By. Let's express the x as a fraction of L, and we obtain the values of Ay and By for various x. By plotting the points and joining them, we have successfully developed the influence line diagram. Next, to develop influence line diagram for internal forces, we need to determine the internal force functions. Let's choose an arbitrary point, namely C, that located at the distance of A from support A. The distance from C to support B is named as B, and by adding A and B, we should obtain L. We have two cases to analyze. For the first case, the internal force functions are valid when the location of moving load x is between 0 and A. The shear force equals to x over L, while the bending moment at point C is A minus AX over L. On the other hand, the limit of x for the second case is from A to L. The derivation of functions is easier for case 2, since the shear force is only based on the reaction Ay, and the bending moment is the product of Ay and A. All internal force functions are in terms of x and A. To know the effect of moving load on the development of internal forces at any possible point, we will need to repeatedly substitute suitable value for A and determine the induced forces considering various load positions. From the developed diagrams, we get to observe that the magnitude of shear force will be the greatest when point C is near to support, but not on top of it. On the other hand, bending moment is the greatest when point C located at midpoint. These influence line diagrams are applicable for all loading cases on simply supported beam. For instance, we are interested in the internal force acting in point C that located at 2 meters from support A. The length of beam is 5 meters, and therefore we should implement the influence line diagram for the case where A equals to 0.4 L. When we have a concentrated load of 10 kN acting at the midspan, the shear force and bending moment of point C can be determined by multiplying the load value with the value obtained from respective influence line diagrams. As a result, the shear force and bending moment are 5 kN and 10 kN-meter respectively. Same approach is applicable to determine the reactions Ay and By, which use 5 kN for both. When the beam is loaded with uniformly distributed load instead, the forces can be calculated by multiplying the area under graph that superimposes the loading with load value. A beam loaded with 5 kN per meter of load over the entire span induces reactions of 12.5 kN for both supports. On the other hand, The shear force and bending moment for point C are 2.5 kN and 15 kN respectively. When using influence line diagram, the sign convention is essential, where the value of influence line diagram is negative if the graph is below horizon and positive if it is above. A series of concentrated load, which simulates the loading from vehicles, is an essential consideration when it comes to bridge design. When we are dealing with such situation, the shear force and bending moment at one point needs to be determined using trial and error method. First, we identify the peak of influence line diagram. Then, we coincide it with the first concentrated load of the series and determine the resultant internal force due to all loads. We will then repeat the process by coincide the peak with subsequent concentrated load. After the trial and error process, we should obtain the most critical internal forces that can ever take place under this loading. We know the maximum bending moment always occurs at the midspan of a simply supported beam. When we are only interested in this bending moment, the procedure can be simplified. First, we determine the magnitude and position of resultant load for the series. Then, we identify the midpoint between the resultant load and the nearest concentrated load. After that, we coincide that midpoint with the midpoint of beam. The bending moment calculated with the aid of influence line diagram will be the most critical among all possible cases. Thank you for watching. If you find this video helpful, please share it with your friends. We'll see you guys soon. Goodbye.